Now I want to talk about microwave ovens and how microwave ovens work. Now we've talked about electromagnetic waves, waves of electric and magnetic fields. I've got a microwave oven here, and it emits microwaves, waves of electric and magnetic fields. And there's a little emitter inside the cavity. And this one, it's right over here. Electromagnetic waves come out into the cavity, bounce around inside here. The electromagnetic waves have an electric field that points one way and then another way. Water molecules have a very, very strong dipole moment. We've talked about that. They got a strong positive end and a negative end. And we've talked about the fact as well that if I have a dipole, it'll rotate to line itself up with an electric field. So the water molecules inside food that you put inside a microwave oven will rotate to line themselves up with the the electric field of the electromagnetic wave. So electric field, water molecule rotates, so the dipole moment of the water molecule lines up like this. Oh, but by the time it gets there, the electric field is now switched. It's in the other direction. And so the water molecule rotates to try to line itself up with the new orientation. Oh, but when it gets there, yeah, it's switched again. And the frequency of the switching is sort of optimized. So if the water molecule rotates and tries to line up with the field, but then the field is switched, and so it keeps on going, and you just have the water molecules doing this. It's trying to line itself up with the electric field, but the electric field keeps changing direction, and so it rotates, and you're feeding energy into it. And then it bumps into other molecules, and that rotational energy turns into thermal energy, and so you heat things up. And water is really, really good at absorbing microwaves because it's got this strong dipole moment. Now I'm going to do a calculation for the microwave oven. Inside the cavity of the oven, it's a 2.4 gigahertz electromagnetic wave, a microwave. It's got an intensity of 5 kilowatts per square meter. Question, what is the strength of the electric field? What is the strength of the magnetic field? Well, we have some relationships for this. The electromagnetic wave has an electric field amplitude that's the square root of 2 times the intensity divided by c times epsilon 0. C is the speed of light. E0, or epsilon 0, that's a constant you know. The intensity is the intensity of waves inside the cavity. That's 5 kilowatts per square meter, or 5.0 times 10 to the third watts per square meter. So I know everything in that expression, and I can calculate what's the electric field strength. If I do that, I get an electric field strength of 1940 volts per meter. Okay? The magnetic field strength, 6.5 microteslas. Magnetic field strength, is that going to do much? That's like significantly weaker than the Earth's field. So this, not doing much. How about this one? 1940 volts per meter. How big an electric field did it take to ionize gas inside this tube? What did we say? 1,000 volts per meter is enough to light the tube. Microwave oven, 2,000 volts per meter, which means the electric field inside a microwave oven is high enough, ionized gases in the tube, i.e. high enough to make this light bulb light. Let's try that, shall we? And by the way, this is, sometimes I do things in class that I say, don't try this at home. This is one. Don't do this. Don't do this. Because there's a whole like putting metal inside a microwave oven on. Don't do this. But if you take light bulbs, put them inside my cavity like so, the electric field is large enough to make the light bulbs light. Then the microwaves will be absorbed by the gas inside the tube. They ionize the gas inside the tube. And let's see, how long do you cook fluorescent light bulbs for? Let's go 8 seconds, shall we? I don't want to cook them too long. And what happens is, the light bulb's light. And what I'm doing is, oh, they're done. Sweet. All done, ready. What you're doing is, I'm applying an electric field to the gases, and I'm ionizing the gases, and I make them give off light. That's what's happening in the light bulbs inside the ceiling. You're putting an electric field across them, ionize the gases, they emit light. And so this is the same thing as what's happening in the ceiling. I'm just doing it with microwaves rather than doing it with the electric fields from the socket that it's connected to. And so there's nothing in principle so wrong with this. As a matter of fact, the bulbs don't particularly heat up very much. when you do this. They're fine. I've done this several semesters in a row, and they survive it. The reason I don't want you to try it is this. I've matched the bulbs to the size of the cavity and the power of the microwave, okay? Because if you put in like one light bulb, the white light bulb is intended to put out like 40 watts, okay? The microwave oven's putting out 600. And it's going to absorb all the energy to get really hot, and then you have exploding light bulbs, and then you have mercury inside your microwave oven. You don't want that. You don't want that. But anyway, I figured out how many bulbs we need, and I've kind of matched this. And so you don't want to try this. But the voltage, or the electric field, is enough to kind of like make that go, and that process is the same as the process right here.